Okay, hopefully the stream started. I need to change the name for the stream. Hydraulic and pneumatic equipment. Cylinders. Okay, hopefully that's fine. Just to be sure, I'm checking if everything is correct there. Okay, yeah, I think we have the right titles for everything now. Okay, so the class for today talks about hydraulic and pneumatic cylinders. Last time we talked about general overview of the systems. So anyways, where's the class? The class is... I'm gonna log in here. Hydraulic and pneumatic systems. Anyways. The main actuators used in hydraulic and pneumatic systems usually are cylinders. There are some exceptions. In hydraulics we may use motors. In pneumatics not so much. So the cylinders usually give us linear movements. That means that we are converting the hydraulic and pneumatic energy into mechanical energy. So by using cylinders we kind of achieve linear motion. With motors we achieve rotary motion. That means that cylinders move in straight line usually, and the motors basically are spinning. So in pneumatics we also have some actuators that are like the rotary cylinders that have the rotary action. That means they are moving from one position to another in making a turn from one position to another. But usually they are not. They have fixed angles, so they are not spinning freely. Motors spin freely for as many rotations as they want to. The rotations is not limited. They can spin basically forever. But rotary actuators, they just move from one angle to another. But we are going to start with the cylinders. So at the moment I have just entered pneumatic cylinder into Google, and you can see there's a lot of different pictures about them. You can see that there are different constructions. Some look like a box. Some look like actual cylinders. Some have some rods on them. Some don't. What is going on? So in this lecture, first I'm going to just go through some of the manufacturers and what kind of cylinders the manufacturers provide us, and then I'll talk about construction of the cylinders, what kind of elements do they have, and then hopefully if we have time left we can start calculating the cylinders. And as for calculations, basically in this class we are kind of only calculating the cylinders mainly. We're calculating the forces of the cylinders and the speeds of the cylinders and if we calculate the speeds for the cylinders, we also calculate the flow rates. That means that we are calculating the required amount of air or liquid to make the cylinders move. So these are the basic calculations we do in this class, and after we are finished with these calculations, we basically don't really add much to the mathematical side. So everything else basically is just an overview of what's going on. So for basically in Estonia, we have the most known providers of pneumatic and hydraulic cylinders are Festa and SMC. So Festa, I think, is the headquarters is in Germany. I think they are they're basically from a German company. And SMC, actually I don't remember it. I think it was originated from somewhere from Asia, but I'm not really sure at the moment. I have some experience with industrial machines. I mean, kind of presses and cutters and these kinds of machines that are used for sheet metal work. And usually the machines that come from Asia, Japan for example, these machines usually use SMC products, and machines that come from, for example, from Europe, usually use Festo equipment. I don't know why they are using one or another. I know that they exist. Also, Bosch Rexroth is common option. Seen those a lot, but Bosch Rexroth pneumatics, for example. I hope we can find it there. Yeah, pneumatics. Bosch Rexroth is also common, but of course there's a lot of other manufacturers that provide hydraulic and pneumatic equipment. Do you know any other providers, for example, from your countries?
No, I don't.
Okay. So at least I've given you 3 options now, so you know, so at least some providers. For example, some manufacturers exist in, for example, Italy. I know there are some French providers. Basically, I think all over the world you can find different companies that produce those parts for pneumatics and hydraulics. I know I have used some tools for industrial robots that we have bought from Italy, for example, and they used totally unknown brands for me, but I think they were some kind of Italy's domestic market producers or something like that. Anyways, a lot of companies provide pneumatic equipment and also hydraulic equipment. Even Estonia actually produces hydraulic cylinders, but at the moment I don't remember the name for the company that does that. Those companies that produce equipment for agricultural means, I mean tractors and everything, like equipment for the working on the field, harvesting crops and everything else. some companies produce their own hydraulic cylinders, for example. Of course, they may use parts from that they are buying from other producers, but the cylinder housings and end caps and larger parts they may actually produce themselves. It may be more efficient for them to do so. But anyways, the actuators, the cylinders. Basically, the cylinders are the main reason we actually want to use those systems. We want to use hydraulic power stations. We want to use compressors, pumps. Because if we don't have an actuator, why are we producing the energy? So generally, the actuator, the cylinder, is the most important part, at least in my opinion. So I'm kind of trying to open up those catalogs for the cylinders from Festo and SMC in parallel, so you can compare the offerings. As we can see that the pictures of the cylinders at least kind of look a little similar. We can see that there are some cylinders that are like box shaped. There are some cylinders that kind of don't look like a cylinder at all. Yeah, there are differences there, but the usual most common cylinder is piston rod cylinders. So if you're going through those catalogs and you're looking for the most common cylinders, it's the piston rod cylinder. And for example, here we can see it's called, in SMC catalog, it's called ISO cylinders. Now, piston rod cylinders, I hope I can zoom in a little bit. The most known or common, or usually people kind of if we talk about a piston rod cylinder, what comes to mind usually for people is the round cylinder. There are some compact cylinders that are just the shape of the cylinder body is a little bit different for the other ones, but the round cylinder is, I think, is the most common one. Is if you think about the cylinder, that's what you're thinking about usually. And here in SMC world, I think it's this C85 series cylinder. It's the most common one. So if we now kind of try to compare, I'm looking for okay, here's the series round cylinder. I'm looking for the catalog. Yeah, catalog is here. Festo catalog, and hopefully we can get some documentation from SMC2. Standard cylinder, English. Okay. Alright. So we have found catalogs for Festo and SMC. And if we are comparing them side by side, this is the Festo one, this is the SMC one, you can see that they are really similar. For example, if you look at that cylinder that's on the left here and compare it to the cylinder here on Festo page, there are not too many differences. They kind of look the same, doesn't they? Or don't they?
Yeah, it looks similar, very similar.
And kind of that's the kind of the reason why they were called ISO cylinders on the SMC page, because there are some standards, ISO standards, that kind of give us the instructions of what kind of cylinders are the standard cylinders that basically every cylinder producer should make. And the standards basically are for the shape, kind of, and for the size of the cylinder. So if we are choosing a cylinder, we are usually interested in the diameter. So how large the cylinder is in thickness. And the other thing we are looking for usually is the length of the cylinder. So the length of the stroke, how far the cylinder piston rod can travel. So the distance of travel and the diameter of the cylinder are usually the two main values that we are looking at. So let's try to go through the Festo catalog a little. Let's see what we can find from here. Oh, we can already see that there are similar construction methods for both of them, as this picture here shows kind of the same cylinders as on the SMC page. From this page we can see the piston as how it looks like and what kind of parameters does it have. The main parameters here are the piston size. So the diameters range from 8 millimeters to 63 millimeters for these cylinders. And then we can see that all the barrels are made from stainless steel. Yeah, all of them. And then we can see that what kind of extras or what are the extra features of these cylinders. Here, for example, the end caps are made out of aluminium. And then this here shows that the backwards end cap is for axial support. That means that it's supported from behind, not from sides. Lateral support, lateral supply port, square piston rod, wow, and clamping unit. Clamping unit basically means that it has a brake, so it kind of clamps the piston rod so it cannot move anymore. It's like a brake on, for example, if we talk about bicycles, we have bicycle brakes. It's kind of like braking the piston rod so it cannot move. Okay. So there are different options for choosing the cylinder, but the most basic one, of course, is the first one, the DSNU model here. What else do we see? There are different features about environment, frictions, the piston rods, corrosion protection, whatever. These are the specifics. The specifics usually should be discussed with the sales representative. So basically the process of choosing a cylinder usually is that you have an application where you need a cylinder, and basically the most logical thing to do is to call the representative and send an email asking them for a cylinder. We have this kind of application. Can you recommend us what's the most appropriate cylinder for the application? That means for example, we have an environment that's really dusty. For example, in environment we are handling timber, wood. For example, we are working in a sawmill where we are cutting the logs into length or doing something like that. That means there's a lot of sawdust in the air flying around. It's dirty. If you describe the environment, describe the needs for the cylinder, the stroke lengths, the forces needed, you can always find an answer which kind of cylinder should be used in the application if you just contact sales representatives. For example, if you're in the environment also may need extra heat resistant values or something. Yeah, basically just we need to describe as precisely as possible the situation we are in, and or where the process or where the cylinder is used. If you can give them a precise description, they can probably guide us through the process of choosing the right cylinder for applications. Yeah, now there are different options. That's just showing us what kind of options all the different cylinders have, and what kind of accessories we can choose for the cylinder. And this page from this catalog is actually quite a nice overview of a cylinder in general. We have options for the cylinder. How do we want to connect the compressed air to the cylinder? Do we just use a coupler that screws right onto the cylinder, or we are using a coupler that has a flow restriction here, the flow control valve built into it? Do we need some clamps for the sensors? So maybe we are using magnetic sensors for positioning. Do we need those? Do we need an extra sleeve on the cylinder for dust protection? What kind of couplers we are using for connecting the piston rods? Do we need ball bearing variation for the connection? Do we just use a flange here, or cylindrical mount here, or straight mount as this one? But this straight mount is a little bit flexible. It's not just screwing onto the piston rod, it's a little bit flexible. It has kind of a rubbery coupler in here, so it kind of flexes a little bit. It's not completely rigid. And then if you're using those couplers, what do we need another piece somewhere where that coupler mounts to? So for example, we have some options of using those connection elements here that can be mounted directly to some object we are trying to move. Do we need guide rails, for example? We can use guide rails. That means that we are removing the rotational factor from the piston rod. Piston rod is the cross section of the piston is basically a circle. That means that there's nothing stopping us from making the cylinder spin around. So basically there's nothing that stops us from going in this motion. But if we use these guide rails, the cylinder is mounted in the middle here, and these guide rails provide us with protection from spinning and additional protection from forces that may be applied from the side. Cylinders are not suited for taking forces from the sides. Cylinders are used for forces that are axial or in line with the piston rod. So that's a really nice overview of different components that we can attach to the cylinders. And of course the catalog continues with the exact models of the cylinders and options for those cylinders. So when we are choosing the cylinder, we are interested in the diameter. So we can see the piston diameters here on top. Then by the diameter we can see what kind of connections we are using for the couplers. So the pneumatic connections range from M5 to 3/8 of a inch, 3/8 inch thread. Piston rod threads range from M4 thread to M16 thread. Stroke lengths start from 1 millimeter and go up to half a meter. And then the pistons do have cushioning inside, so we can talk about it later, but that means that when the cylinder is moving, it has internal kind of a smoothing element that tries to stop the cylinder from hitting the end of the cylinder, the end stroke of the cylinder, straight on. It tries to slow down the cylinder before it reaches its end position. So that's the cushioning basically. And there are different kinds of it. Fixed cushioning, adjustable cushioning, and automatically adjusting cushioning elements. And for example, here it also shows the length of the cushioning areas. And I think the first cylinder, the smallest cylinder, actually doesn't have any cushioning. Mounting position. Some cylinders may specify only in vertical positions or only in horizontal positions. This cylinder can be mounted in any position. Up, down, vertical, in an angle, whatever. Doesn't basically this cylinder doesn't care. Okay, so we kind of have some idea what kind of parameters we can see for the cylinders if we're choosing one. The SMC catalog basically has the same options available. Basically the style of the catalog is a little different, but the information we get from the cylinders is almost the same. It also describes the types, the pressures, pore sizes. Pore size is the diameter of the cylinder. Stroke lengths, here for example maximum stroke length is 1000, that means 1 meter cylinder length. What that's a long cylinder. And if we have some cylinder specifications that are not regular, usually the manufacturers are able to produce custom cylinders too. for example, the maximum stroke length here is 1000, but if we actually need 2000 millimeters, it may be possible. You can order a custom order too. I'm not sure if we saw these values somewhere in the Festo catalog too, or are they provided somewhere. But here, for example, in SMC catalog, we have two quite important values here: maximum operating pressure and proof pressure. Maximum operating pressure means that in this pressure range, 1 megapascal, which is 10 bars of pressure, in this area, the cylinder will be able to work. We can use 10 bars of pressure. The proof pressure means that if for some reason we have a pressure peak, the pressure rises for some reason to high levels, 15 bars of pressure, the cylinder will not explode yet. So that's the proof pressure. But if we go over this value, for example, we have 2 megapascal, 20 bars of pressure, the cylinder may actually break and it, quote unquote, it may explode. Anyways, and what's nice about those catalogs is that they also provide us with the correct symbol for our schematics. So if we want to use this cylinder in our schematics, the correct way how to describe the cylinder is given here. So we can show these cylinders on our schematics. That's nice. Okay, but how do cylinders actually work? Paint. Yeah, paint. How do cylinders actually work? So let's say this is our cylinder. The construction of the cylinder. The most important part of the cylinder is its bore, the cylinder body. And usually it's exactly what it's called, it's a cylinder, a round tube. The cross section of the cylinder is usually round, and it has some length, therefore it's a cylinder. Cylinder has end caps. That means that these are the caps that close the front end and the back end of the cylinder. These come in different shapes and sizes, as you saw from the catalogs. There were round ones. There were some that had some cutouts and whatever. But usually these end caps provide us with the input ports. The ports, basically holes that are used for letting the compressed air or hydraulic liquids, in case of hydraulics, into the cylinder. So cross section of the cylinder kind of looks like this. So the compressed air can enter the cylinder from here, if we are talking about pneumatic cylinders. And the ports are on both ends of the cylinder, in the front end and in the back end. So this is the front end cap and this is the back end cap. Which one of them is the front end cap and which one is the back end cap? This distinction comes from which side the piston rod is looking out from. So, or hanging out from. So if this is the piston rod and it sticks out from the left side here, this is the front end, and this therefore is the back end. So inside the piston there is or the cylinder there is the piston rod, and of course the most important part inside the cylinder bore is the piston itself. So the piston is the element that actually produces the linear movement. It's the most basic part that moves here in the piston, in the cylinder. And the piston rod is connected to the piston. Therefore it's called the piston rod. Basically it's just a rod, a straight element that's connected to the piston. Yeah, okay. I just remembered where we had. I don't have to draw it by hand. I have actually a I think a cross section or the picture of it in Moodle. Moodle. It should be in the first set of exercises. Hydraulic and pneumatic systems. Okay, found it. I'll open it up. Pneumatics, first set. So in the Moodle it should be the laboratory work first set, pneumatics. And yeah. Here we have the cross sections for the cylinders. So this is basically a cross section of an actual cylinder. So we see that the piston is this part in the middle. That's the second part here. That's the piston. And piston is inside the barrel. The barrel is the third part here. And we have the end caps, back end cap and front end cap. And the end caps have those holes inside them. That these are the ports that we were talking about. The gray part here, this is the piston rod. And the piston rod goes through the front end cap, and front end cap usually has also the bearing that supports the piston rod when it's moving from one direction to another. And it also has the seals that seal up the cylinder here. So if the seals are fresh and new, they will at least they will try to seal the compressed air. But when they are worn, they may start leaking compressed air. So of course the other seals, when they are worn, they start leaking, but usually, if possible, we try to use the back side of the cylinder for the actions where we need the cylinder to move, because when we pressurize the back part, we have more seals in front of the compressed air before the end cap, so less likely to leak from the back side than from the front side. And we have more seals that are stopping the leaking process. So anyways, so these black parts everywhere we can see around the cylinder here, these are the different seals used in the construction of the cylinder. So we can see there are also some little seals in the end cap here where the barrel meets the caps. So these are of course needed for sealing the cylinder end caps. And we can also compare the cutout to the schematical element, how we are picturing this in schematics or drawing those cylinders on the schematic. We can see a lot of similarities. The main what's it called, rectangle, or the main rectangle here shows us basically the body of the cylinder. The smaller one here is the piston rod. The other rectangle here, this is the piston. The smaller ones near the piston, these are the cushioning elements. Actually, these are shown here on the cutout too. This C-shaped element here means that this piston has a magnetic ring to it. That means we can use magnetic sensors for detecting the position of the cylinder by using magnetism. And this arrow here means that the cushioning part is actually adjustable. But the most basic parts of the cylinder symbol is the main rectangle, the piston, and the piston rod. And of course, these small lines here, these are the input ports, the connections for compressed air or hydraulic liquid, if we are using hydraulics. But what makes the cylinder work? If we take the cross section of the cylinder, we are putting in compressed air from this side, for example. The compressed air is going to fill up all the empty parts of the cylinder here. And basically, the compressed air will start to push on the piston. So if we look at the piston from the side, the piston cross-section is a circle. Unfortunately, I was not able to draw a circle here, but let's kind of imagine that this is a circle. The cross-section of this piston is a circle. The compressed air is going to be applied on the piston cross-section, and by applying the compressed air, or in hydraulics the liquid, to the piston, it generates force in 90 degrees to the piston cross-section. So basically it will generate force in the direction of the piston rod, and that's what makes the piston move, the force that is generated there. So for example, in this picture, if we want to make the piston move out, so we want to move the piston rod out of the cylinder, we need to put compressed air in from this side. This generates force. Force starts to move our cylinder, and the cylinder moves to its end position here. When the cylinder is moving to its end position, this part of the cylinder is actually usually filled with compressed air too. Or at least either it's compressed air or the hydraulic liquid, or it may be even atmospheric air. The pressure actually doesn't matter here, but the point that there is some liquid or air in this part of the cylinder, that's important. That means when we are putting in some compressed air or liquid from this side, we also need to release it from the other side. So to make this exact cylinder work, we need to put compressed air in from one side and let it out from the other side. So when that makes the cylinder move out. And to make it move back in, the process is exactly the opposite. If it's if the cylinder is in its end position here, the rod is fully extracted. To make it go back, we need to put air in from this side and release it from the other side. Construction-wise, this cylinder is the easiest cylinder to construct. It has the fewest parts, at least for a piston rod cylinder. And the construction-wise, it's easier to make this cylinder. But controlling or making it move, it's not the easiest, because exactly the reason that when we are putting the compressed air in from one side, we need to get it out from the other side. And we have to switch those operations exactly around to make it opposite. Easier for control, but a little bit more difficult to produce, is this cylinder. This cylinder is called single acting cylinder. It looks similar to the previous cylinder. In general, it looks the same, almost. On this picture of, or the cross section, we also see the magnet here, which I was talking about earlier, the magnetic ring that we can use for the magnetic sensor. It actually existed on the other cylinder too, but it wasn't shown. But construction-wise, we can see that there is something going on here. There is something that's put over the piston rod. What is that thing? Do you know what?
I don't know, what is it?
That's a spring.
Yeah, okay.
That's a spring. Actually, two of them, a larger one and a smaller one, both together, put on the piston rod. And if we compare it to the previous cylinder, we actually don't see the port here. There is a port on this side, but not here.
Yeah.
Yeah. So, construction-wise, it's a little bit different and a little bit more difficult to produce because of the spring part here. But to control this cylinder, it's easier. This is a single acting cylinder because we are only using compressed air on one side, on the left side here. So only thing we need to do, we need to put in compressed air from this side, so the cylinder moves out. And if the cylinder is in its final position, the piston is here and the rod is fully extended, if we want to get the cylinder back to its starting position, we will just release the compressed air from that side. So compressed air in, compressed air out from the same side, and that's the only thing we need to do. And that's quite easy compared to the previous version, where we had to release the air from the other side and then switch around. So control-wise, it's easier to control this cylinder. Because why is there that spring? The spring will push the cylinder back to its starting position. So when we release the air from here, from the backside, the spring will push the piston back. But what about that air that's on this side? Don't we need to kind of exhaust that too? Actually, we are exhausting that air through the smaller hole here. And that's basically a breathing port that just breathes this air in and out from this side. So we are not trying to compress air in this part, and we are not generating vacuum here. So air can travel through this side in both directions. But we're not using compressed air on this side, only on the left side, only on the back side. So this is a single acting cylinder, and the name comes from the single action on this side. So we are using compressed air only on one side. That means that it's a single acting cylinder. The other cylinder I was showing you before, previously, this is a double acting cylinder. And the reason is we use compressed air for both movements. On both sides we use compressed air. Therefore it's double acting. Okay. So the pressure basically is the reason why those cylinders work. The pressure applied on the piston. The pressure generates force. Force makes the cylinder move. But the pressure is not the only value we are looking at. Pressure just gives us potential to move, the force. But when the cylinder starts to move, the volume that we need to fill here, this area here starts to expand. And on the other side, of course, this area here is going to get smaller. That's exactly the thing. We're putting air in from one side and releasing it from the other side, because here on the right side we're pushing it out because this area here, this volume here gets smaller, and we're letting the air in from the other side, and it flows into the cylinder. When the cylinder moves, this area or this volume here gets larger, so we need to fill it. So basically we have pressure and we have volume. We need to have some flow into the cylinder. We have volume of liquid or volume of air that needs to enter the cylinder to make it move. So in total we have two basic values that are needed for the cylinder to work. The one and kind of the most important value is the pressure, and the other is flow rate. Pressure gives us force, flow rate gives us speed. And if we are familiar with the mechanical power, the power is pressure times quantity, the flow rate, and it basically is speed times force, which should be the power, mechanical power, if I'm not mistaken somewhere. Anyways, these two values are the values that make the cylinder work. But now, of course, to understand how they actually work, we have to understand the pressure and we have to understand the flow rate. What is pressure? How to measure it? What kind of scales of pressure we have? And also, what is flow rate? How do we measure it? What kind of scales of flow rate we have? and so on. So we do have some time left, and we will start to talk about the pressure, and then we'll talk about the flow rates.
Okay.
After the pressure. Yeah.
Okay.
Did you want to ask something?
No.
No, it's okay for me.
Okay. So we'll discuss the pressure and flow rates and how they are related to the operation of the cylinder. So, pressure. First of all, the scales of pressure. So, I'm not really sure about this horizontal axis, but the vertical axis, let's say the vertical axis is the axis of pressure. The pressure. So usually one pressure we are experiencing every day, and actually we should be quite familiar with, is the atmospheric pressure, the air pressure. If you look at the weather reports, you can see that usually we have like humidity, temperature, and air pressure as the signs of the weather. And of course, the air pressure, the atmospheric pressure, can fluctuate throughout the day, throughout the months, whatever. But let's say here in this example, let's say it's constant pressure. The constant pressure is I may remember it incorrectly, but I think it was the air pressure was 101,325 pascals of pressure. Pascal is a unit of pressure. We'll talk about it later. I think it was the air pressure was something like that. Then, if that's the atmospheric pressure, 1 atmosphere, nominal value for it, then in technical terms we use a pressure unit that's called a bar. That's not a bar where you go to have a drink, but it's a bar of pressure. Bar is 10 on the power of 5 Pascal, which means it's 100,000 pascals. So in technical world, we are usually saying that 1 atmosphere is basically 1 bars of pressure. Okay. So this black line here, this is the air pressure, the atmospheric pressure. So it basically is 1 bar of pressure. It's 1 bar of pressure compared to the absolute zero, absolute vacuum. So if we're talking about absolute values in absolute scale, this is the air pressure 1 bars of pressure, absolute value of the pressure. If we have a pressure inside the system that's higher than the atmospheric value, then it's called the overpressure. And for example, if you have additional bar of pressure here, so let's go 1 bar higher. So if you're talking about absolute scales, this is the absolute. Absolute pressure. Then in absolute scales, the atmospheric pressure is 1 bar of pressure, and 1 bar higher than the atmospheric pressure is 2 bars of pressure. That's the absolute scale, starting from absolute zero. Usually in hydraulics and pneumatics, we are actually using relative scale. That means that when we go 1 bar higher than the atmospheric pressure, the gauge, the pressure gauge we are using is actually showing just 1 bar of pressure. Not 2, just 1. And this 1 is relative to the atmospheric pressure. That means we are using relative scale. So the pressure gauge or the manometer shows us 1 bar of pressure. When the system is at atmospheric pressure, there is no compressed air in the system. The gauge shows us 0. That 0 doesn't mean that there is no air. It just shows that relative to atmosphere, there is no difference. There's just atmospheric pressure in the system, therefore the gauge shows 0. If we raise it, it starts to show. If we raise the pressure over the atmospheric pressure, it starts to show pressure values on the positive side. And if we go below, it starts to show values in pressure in negative side. So for example, if we go down from the atmospheric level, it starts to show negative values like these, like for example minus 0.5. That means we have minus 0.5 bars of vacuum pressure in relative scale. 0.5 is maybe not the best example here. Let's say we have 0.7 bars of vacuum pressure in this point, for example. On relative scale, this is 0.7. On absolute scale, it's positive 0.3. So hopefully the difference between absolute and relative scales is understandable. Absolute pressures always start from the absolute zero, and relative pressures start from the atmospheric pressure, relative to atmospheric pressure. I hope that concept is understandable. So the usual values that are used, or the units that are used to describe pressure, the 1 Pascal is the basic unit of pressure. 1 Pascal is 1 Newton of force on 1 square meter. Sorry, I messed it up. Not millimeters. Newton of force over square meter. So when it's Newton over square meter, then the calculation would be force over area. So the calculation for pressure is P, pressure, equals force over the area, or force divided by the area. Newtons divided with square meters. That's the main unit of pressure. If we talk about SI units, then we have Pascal, we have kilopascal, and we have megapascal. We usually don't use kilopascal, we usually use megapascal. Megapascal is 1 million Pascal, which means that 1 million newtons of force over 1 square meter. But if instead of meters we use millimeters, 1 megapascal is newtons over square millimeters. And now we're getting somewhere. In calculations, my recommendation is always to use megapascals. Because if we use megapascals in calculations, we already have millimeters as an unit. And usually when we calculate hydraulic and pneumatic systems, we are interested, for example, in the size of the cylinder bore size. So the piston size may be, for example, 10 millimeters, 16 millimeters, 50, 40, 63 millimeters. We are usually interested in millimeters as a unit, and megapascal already has the units in millimeters. Therefore, this is recommended to use in calculations. But it's not the standard unit, but we do use it. It's the bar is the unit of pressure, and bar is 10 and the power of 5 Pascal. That means bar is 100,000 Pascal. Megapascal is 1 million Pascal. Then usually, for example, we have the system pressure in the pneumatic systems usually is around 6 bars of pressure. If we want to convert that into megapascal, how many megapascals we have if we start with 6 bars of pressure? What's that in megapascals?
0.6.
Yes, we have to divide by 10 to get to the megapascal values. So that's basically usually if we talk about calculation of the cylinders, that's usually the only conversion we have to do. Just we go from bars to megapascals, and all other units will match, and the calculations will be correct in the end. So, for example, previously I said that the value of pressure is force over the area. I'll have a new sheet now. So the pressure equals force over the area. Usually in choosing the cylinders, if we are choosing the cylinders, we are usually interested in the force of the cylinders. So, for example, if we want to rearrange this equation for calculating force, how would this equation look like? Force equals
area multiplied per pressure.
well, yeah, that's for some that may seem funny a little bit. So, just not to be rude, we can arrange this also as force equals pressure times the area. Otherwise, it's basically masturbation. But anyways, jokes aside, but my own experience has shown that usually when we have this equation written out as this, then people usually remember it better than in the other way around. This way usually be anyways, yeah. I've basically taught this course for almost 10 years now, and I started out with this version, and people tended to have troubles remembering this equation. It's only 3 elements in this equation, but they were struggling remembering this. But when I started using the other version, for some reason, suddenly people remember it better. Anyways, okay, so pressure times the area. Let's have a example from the class, from the lab. The cylinders we use are of a diameter of 20 millimeters, and the pressure we use is 6 bars of pressure. 6 bars was 0.6 megapascal. And the area we calculate is the area of the circle. But what's the calculation for the area of the circle? The equation for the... Well, usually it's pi times the radius. Pi squared. Pi times r squared is usually the equation people remember. But we can rearrange this equation a little bit to have it in the form of pi times diameter squared divided by 4. This version is easier to use because basically only number we have to insert into this version is the number here, the 20. We don't have to separately divide it by 2 to get the radius. So, if you would like to calculate the output force of the cylinder we use in our lab, we have pressure of 0.6 megapascal here, we have the pi, we have the diameter 20 squared divided by 4, and in return what that equals to. Can you calculate it? I can say it's over 100, close to 200.
1884.
Yeah, 1884
Yep.
newtons. That's theoretical maximum out of this cylinder. So if we translate this to kilograms, it's about 19 kilograms of force. So basically, if we're in the lab and the cylinder is moving and for some reason someone gets hit by that cylinder, the person will experience getting hit by 19 kilograms of force. Well, usually that doesn't happen, that someone gets hit, but theoretically it's 19 kilograms of force. Well, it hurts, but usually it doesn't kill, at least in these numbers. In hydraulics, I'll just make this comparison just for the food of thought to end this lecture. In comparison, in hydraulics we use quite a lot higher pressures. The cylinder size may be the same, but the pressure is higher. So in the lab, for pneumatics we use 6 bars, for hydraulics we use 60. And in industrial environment we can see 120 and, for example, even 600 bars of pressure. So in the lab, if we take the lab as an example, the pressure is 10 times higher. That means if we look at the equation, the result is 10 times larger. That means that in hydraulics, instead of 19 kilograms of force, we now have 190 kilograms of force. And that kind of is getting a little bit scary, isn't it? So basically, if we use hydraulics in the lab, we need to be a little bit more careful of what we do. Because so far no one has hurt themselves. Only I have hurt myself. I usually show that don't do this, and then I got caught in something and there's blood everywhere, and anyways, so you can sometimes it happens, but at least none of the students have hurt themselves. But just to remind that dealing with hydraulics in the lab, we are dealing with quite a lot higher pressures and higher forces. But pneumatics is kind of safe. Anyways, next time probably I'll continue with this explaining the forces and the pressures. I'll go over the flow rates too, and then hopefully I can start to talk about how do we control the cylinders, what kind of elements we need in the systems to make change the directions, speeds and forces for the cylinders. And then we are almost there to go to the lab. I think we have 1 or 2 lectures more before the lab.
Okay.
Well, currently I don't remember how many lectures we have before, but I think it's 1 or 2 lectures. And I'm 1 lecture short, so I'll record it sometime. I think after the last theoretical lesson I will record another extra lecture, and before coming to the lab you can watch that lecture too from on YouTube. So basically you can search for my channel And you will basically, you will find it. Also, I'll probably send you the link for the lecture then. So you just should search my name, and you'll probably find my channel. And you may also find some other interesting things around here. So, okay. Thank you for your time. Thank you for listening, joining this lecture. We had some hiccups with starting it, but otherwise it went quite well, I think. Do you have any questions or something other, some other things to discuss?
No, no questions.
Um, uh, During the lecture, I tried to think of other companies, but at the moment I just could not remember any other companies to suggest. But if I come up with something, then I'll let you know.
Okay, thank you very much.
Okay,
Okay, thank you.
Bye.
bye.
Bye.